Okay, this is a really funny joke. You guys ready for it? Okay.
I want to.
Okay, why can't pirates finish the alphabet? Because they get lost at sea. In this video, we'll focus on reflected light from curved mirrors. We have two types of curved mirrors, concave, which are also converging mirrors, and convex, which are also known as diverging mirrors. We'll take a look at each one separately. Sylvie, right, are you in the spoon?
No.
No, I can see you.
No.
I can see me. I'm upside down. Where are you, Nora? Oh, Nora just came in. There she is. She's upside down too. You're all upside down. Hey, you're upside down. Now you're right side up because you're upside down, actually. Nice.
Me.
To determine imagery in curved mirrors, we definitely need to determine where the focal point is in these curved mirrors, whether they are concave or convex. Our next little video will show you how you can determine the focal point using a simple ray box design. Similar to our plane mirror, the first thing you'll need to do is trace out the shape of your concave mirror with a pencil. You can see 5 parallel rays being shone through this ray box and onto the concave mirror surface. Now you can also see where the focal point is, and in the next little clip I'll clearly mark that off using a pencil. Now you can see where I placed the dot, that's the focal point, right where all those rays, or reflecting rays, are intersecting. Now that focal point is also indicating that this is definitely a converging mirror. All the lights reflected rays are coming to a single point, that focal point. The concave mirror is surely more complex than the convex because you have 3 different possibilities. In this first possibility, we have an object, George, that is between the focal point and the mirror surface. Let's see what happens. When an object is between the focal point and the concave mirror surface, you will see an image that's larger than the object, an image distance that's further from the mirror itself than the object. The image will be upright and it will be virtual, meaning it's going to appear to come from inside the mirror itself. In the second scenario, the object is between the focal point and twice that of the focal point, which is also known as the center of curvature for the mirror. Let's see what the theory holds here. So when the object is between the focal point and twice that of the focal point, you'll see the image characteristics as follows. The image will be larger than the object. The position will be larger than the object's distance is from the mirror. The orientation of the image is inverted, meaning it's flipped over compared to the object. And the image is also real, which requires a screen to see it. In the last scenario, the object is further than twice that of the focal point from the mirror's surface. Let's see what happens in this situation. When the object is further from the mirror than twice its focal point, the size of the image will be smaller than the object. The position will be closer to the mirror's surface than the object is. The image will be inverted, flipped over compared to the object, and it will also be real, again, meaning you'll need a screen or something to capture that image. It won't appear to come from the mirror itself. Now you're normal. I'm not upside down. You're not upside down.
Yes.
Nora's not upside. Well, you are upside down, but you're not. Your image is not upside down. Nora looks normal.
Upside down.
Yes. There it goes. So when light hits a convex mirror, you can see that the reflected light will be divergent. It will never intersect. In order to see where it will intersect, we need to virtually bring those reflected rays into the mirror surface. And that's how we establish the focal point. Again, we must trace the shape of our mirror, our convex mirror this time, and then we'll be using a ray box to see what the light does when it hits that surface. So using the same 5-slit apparatus as our concave mirror, you can see now that the reflected light is diverging from the mirror surface. Very faint rays, but you can see them definitely spreading apart as they go away from each other. And here are my little pencil markings indicating the reflected rays. I just need to straighten them out using a ruler and then extend them into the mirror surface to determine where the focal point is. So all of the extended reflected rays came together fairly cleanly, although there was a little bit of error. Now we got a pretty good diagram from which to draw some reflected imagery. Convex mirrors simply give us just one set of spot characteristics. Regardless where the object is, the image size will always be smaller than the object. It will always be closer to the mirror surface than what the object is. The image will always be upright, and it will always be virtual. It will come from inside the mirror. So here is our real diagram showing the object and the image within the mirror surface itself. You can clearly see the spot characteristics are as they were established on the previous slide. So here you can see the back of the spoon being used as a convex mirror, showing the same image characteristics that we just saw.
Upside down. Upside down. Yeah. Normal.
Normal. Okay, that's curved reflection.